I think so. Hi everyone, I'm really happy to finally be here in person presenting the work of my colleagues and I on the compositional verification of smart contracts through communication abstraction. So hopefully by the end of this talk, we will be able to all understand what this long string of words actually means. So that being said, I guess let's get straight into the talk. So I'm going to start with some background and motivation for this work. So what smart contracts are and why we care about verifying them. So I guess there's a lot of different ways you can define smart contracts. In this talk, we're just going to assume that, think of smart contracts as some finite state machines. They manage assets on a blockchain. So we don't really too much about how a blockchain works. I guess by now, everyone's probably heard of blockchain, just in case you haven't. They're kind of like databases that ensure some guarantees of consistency. So a fairly reasonable memory model. And often these smart contracts describe financial agreements. So one of the examples for this talk is going to be an open bid auction. So this auction starts in some winning state. Users can come along and place bids into this auction. Eventually some special designated manager can stop the auction. And then once the auction, something on?
We're not sharing the slides online, sorry.
Oh, okay.
It's,
I guess the technical difficulty.
1 second, I'll be right out of your hair.
No worries.
So this seems to be sharing. Interesting. It should share the entire screen, which means
Can they see it online now? Can you see it? So I guess I'll just take a step back for people who came in. So right now we're just kind of defining what a smart contract is. We're thinking of these as finite state machines, and our winning example is going to be an open bid auction. Users can come along and place bids until some manager stops the auction, and then once the auction stops, anyone who didn't have a winning bid is allowed to withdraw their bids. And one popular language for writing these smart contracts is called Solidity, and that can be thought of as a way to facilitate information flow between all of these users. And an important thing about this is all of these users have unique addresses, and these addresses don't change, so we can uniquely identify all of the users interacting with this finite state machine. And just to give an example of a Solidity smart contract, we'll go into more detail in a moment. We can see on this right, this program here, this is just like the interface, and it's kind of like an object-oriented program. These contracts are like objects. We have regular constructors. Each of these transitions of the finite state machine is given by a function, and these functions execute atomically, but the order isn't necessarily guaranteed. So why do we actually care about verifying these smart contracts? So I'm just going to walk through a scenario that kind of describes how a Solidity smart contract usually is developed and interacted with. So in the beginning, some developer is going to sit down, they have like maybe a financial agreement in mind, and they codify that agreement as a smart contract. So once again, our one example was an auction, but there's many other cases, maybe like a money transfer service or something like that. And once they're done, we have this smart contract that's essentially a financial agreement. These can then be deployed to a blockchain like Ethereum, and then once it's deployed, this code is immutable. That means that if there's a bug in the code, no one can come back and fix it. So the code has to be correct as soon as it's actually deployed. It isn't usually the case with most software. And then this smart contract allows users who don't really know each other and have no reason to trust each other to engage in collaboration financially, and the smart contract is supposed to enforce the interactions between them that they would expect. So this means that the code actually has to be correct, and these users will all want to know that the smart contract has been verified. It's possible that the developer might be malicious or a user might be malicious, so ideally any one of these parties should be able to verify the smart contract if they want. So a good solution here shouldn't require like a verification expert to sit down and actually verify the smart contract. So now that we have the problem in mind, let's take a step back and actually look at what these smart contracts look like. So this is just a fragment of the auction example that we looked at in our paper. Some of the things I had mentioned before, like the idea of a manager keeping track of the bid and whether it's stopped, these are these variables in this class or contract, whatever you want to think of it as. And one important thing is that these are zero initialized, so we know the initial state of this contract. And one other thing to point out is we have this address variable here. When it's zero initialized, that can be best thought of kind of like a null pointer. We have a special address that means that no user is being designated yet, kind of like saying that at this point there is no manager. We also have these structures called mappings. They're kind of like maps or dictionaries in most other languages, but they start off at least from a conceptual point of view, the entire map's initialized and all entries are zero. So really big structures, and we'll come back to that on the next slide. So once you deploy the smart contract, this constructs the ones and gives an initial state. So throughout these slides, we're going to just be representing these states and transactions using these kinds of block diagrams here for simplicity. So in this example, this is a saying that someone called the constructor. The person who sent this request has address 10. And you can also attach money to these transactions, so that's just saying this has a value of $0. And then every other transaction is just going to be a function. One important thing here is that we can have these require statements, and there's not one here, but we can also have assert statements. So the contracts are usually written with some specifications given. And one special line here is that we check that the sender is not the manager. So this ensures that the person running the action isn't able to submit a bid on their own behalf, like maybe artificially inflating the auction. And throughout these slides, we're sometimes going to think of long running processes. So we are going to also use some notation to summarize possible states. So for an interval, we just have this dot notation. So this says that the auction is either stopped or not stopped. Well, and for values where we want to correlate two cells, we're going to just use symbolic variables. So this is saying that the leading bid is designated by B and it's non-negative. And then each of the bids is between 0 and that leading bid value of B. So why are these hard to verify? So the states, smart contracts actually have a lot of uses. So the address space actually has a size of 2 to the power 160. So that means that this conceptual map here actually has 2 to the power 160 cells. And these monetary values are by default of the size 2 to the power of 256. So this, if you're just going to actually try to enumerate these states, this state space is definitely intractably large. And also these smart contracts are usually long running. The sequence of transactions is often unbounded, and if not unbounded, intractably large. I won't go through this calculation, but if you want to sit down and work through it, this smart contract, for example, can have sequences of transactions of lengths up to 2 to the power of 256 plus 2 to the power 160. So also really long traces of transactions to enumerate as well. So there's many solutions that already exist to verify these smart contracts. I'd like to take a step back and say that this slide was actually written in 2021, and I'm not really working on smart contracts anymore. So I can't guarantee that what I'm saying is completely up to date, but this was at least the state of the art while we were working on it. So there's a spectrum of techniques. On one end, you have what we categorized as declarative static analysis and dynamic analysis. So these include things like data log that might define some rules of what a bad smart contract looks like, or other techniques like fuzzing. And they're easy to apply to many smart contracts because you're just kind of looking for bugs, and like a failure of the smart contract, you don't really have to specify anything else. But as I said before, they're limited to bug finding. So we can actually verify correctness from that. Another common technique is using model checking and symbolic execution to check the pre and post conditions on each transaction. That's usually, these tools are usually quite efficient, but the properties only look at single transactions. Moving up from that, you can put invariants on the state of the smart contract, so these should be true over every sequence of transactions. So if you're used to object-oriented verification, you can think of these like object invariants, or if you're coming from a model checking background, like maybe LTL specifications on a state machine. And then on the farthest end, we have, so I guess one thing to add is that these techniques allow for deeper properties of smart contracts to be verified. So going back to the auction example that the leading, as I kind of implied in the beginning, the leading bid should be tracked by the smart contract, and that should be true over every sequence of transactions, no matter how users interact with it. But these techniques are usually harder to scale to large smart contracts, and they require additional specifications. And on the furthest end, you can actually just write a proof by hand to show that the smart contract is correct. So these are great because they prove total correctness, but if you're actually going to do that, you have to be a verification expert, and that's not the kind of problems we're targeting here. So in this work specifically, we look at contract invariants, and we try to deal with the issue of limited scalability coming from the size of the state space and also the number of transactions we have to deal with. So with that being said, let's take a look at how we address this problem. So if you come from a background in parameterized verification, it's often possible to take these systems of arbitrary size and look at a few users or clients and then generalize the proof to any number of users or clients or maybe array cells. And even though these smart contracts aren't parameterized, we thought that maybe you could do the same kind of proofs for these smart contracts. So we start by generalizing these smart contracts like a network perspective. We think of the state of the contract that isn't indexed by addresses as kind of like a control process that takes and handles requests. And then when you have a mapping from addresses to data, that can be sort of the state of some user process. So now we have some parameterized, and we also think of there being now n addresses rather than 2 to the power of 160. So now this is some parameterized network where n is the number of users interacting with the control process. From there, our next step is trying to understand how these clients can interact with data in a single transaction. And we'll come back to that in more detail on the next slide. So what we actually do is we try to identify groups of users that can communicate together, and the users in these groups are kind of like interchangeable. So you can think of that kind of like an equivalence relation over these users. So in our example, as I mentioned before, we have a special address to 0 address, and that behaves differently than every other user because it can't send requests. We have the auction itself, which is the control process, the manager that isn't allowed to place bids, and the state of a single sender sending request. And this would vary depending on the smart contract. So for example, if you had a smart contract where you're sending money from one user to another, you'd have an additional user over here. And let's just focus on this auction example for now. And then our idea is to use these representative users to try to do some kind of abstract analysis that generalizes. So for example, if we have a user placing a bid of 10, we now know that we have a user with a bid of 0 or a bid of 10, and then you can abstract that just thinking of some value from 0 to 10. We're not just going to use that kind of abstraction, but for the sake of this example, let's just think about an interval. And to understand how this actually helps with verification, let's look at a specific example. So we're going to try to prove that the bid of each user is at most the leading bid, but to do this, we're going to have to provide some abstraction for each of these users. We call this an interference invariant, and that relates the state of an individual user in a group back to the state of the control process. So it turns out that in this simple example, we're actually able to use the property we want to verify as an interference invariant as well. So let's see how this works. So we start by constructing the smart contract. In this example, I fixed the inputs, but you can imagine just enumerating the few addresses we have in this abstract set of users. And then you can think of some user placing a bid. Let's say, in this case, we have a bid of 20. Then we can look at each of these users and make sure that this property still holds. We see that the bid of each user is either 0 or 20, which is less than the recorded leading bid of 20. Since this checks out, we can then use our interference invariant to abstract the state of each of these users. Now they each have a bid from 0 to 20. And then we can use some technique like model checking to compute an over-approximation of the state space, and we can find, using the tool we implemented, for example, that the leading bid is going to be some non-negative number. Each user is going to have some bid between 0 and that leading bid, and the auction is either stopped or not stopped. And thus, by this correlation between the leading bid and the state of each user, we can then infer that the bid of each user is at most the leading bid. There we go. So let's take a look at how we actually implemented this in practice. So in the previous example, I kind of argued by hand how you find, manually how you would find this group of users for the auction, but we'd like to have that automated. So we introduced this idea of participation classes. So there's different ways users might interact. So for example, if I send a request to a smart contract, that would be like a direct interaction in a transaction. Alternatively, there might be like some implicit communication, like I might check that the person sending the request isn't the manager, so that's another kind of participation. And then we proposed an algorithm called PTG Builder that uses data flow to actually identify all of these possible interactions that could influence the outcome of the transaction. And that would give us this group of users that these different groups of users that I talked about in motivating example. So this is automated. The details of the algorithm aren't really that important, but you can find them in the paper if you're interested. From there, we have what we call, and I guess this is the key point of the talk, this local bundle abstraction. So that takes our participation classes, a smart contract, the interference invariant I talked about before that abstracts the state of each of these groups of users, and then this spits out what we call a local bundle. So that's so now that we have these transactions that we know are atomic, and we have this small set of abstract users, this essentially just gives us a sequential program, specifically in C, that simulates any sequence of transactions up to some unbounded length. And so in a preceding example, this abstraction would reduce us from 2 to the 160 users down to 4. And then the model we're generating is in C, so we can use an off-the-shelf model checker like C-Horn for C programs to check that this program is actually safe. And C-Horn is an unbounded model checker, so that already deals with the fact that these sequences of transactions can be unbounded. And then we can get one of two outcomes. Either the program is safe or the result is unknown. Usually you'd have either safe or unsafe, but the problem here is that these interference invariants are, well, there might not actually be an interference invariant to prove that a program is safe. So this is more like whether or not a proof exists given the abstraction we gave. In this work, the abstractions are given manually. In future work, we have looked into automating that, but that's outside of the scope of what we did in the 2021 work. I can talk about that more afterwards if anyone's interested. But one thing that I think is worth talking about is whether you actually get back when a proof doesn't exist, given the interference invariant. So C-Horn actually allows us to generate an executable counterexample. So this lets us actually run a sequence of transactions and concretizations that would actually violate the property. So let's say, for example, I gave an inadequate interference invariant in my example that the bid of each user is at most 10. So let's see what that counterexample would look like. So we could start by constructing the contract in the same way I did in my example. Then we abstract the state of each user. Now they have bids from 0 to 10 because that's my interference invariant set. From there, we can just select some concrete values for these users. Then let's say one user sends a bid of 20. We can see that that violates the interference invariant, and then this is generated, given back, you can run it. I'm using this diagram because it's a bit easier to follow, but essentially would this give like a textual representation of what I went through here. And then to make sure that these techniques were actually solving the problem better than existing techniques, we compared to a state-of-the-art smart contract verifier called Verx. Once again, I'm not sure if that's still the state-of-the-art because I'm not working in the area anymore, but at least at the time it was. So we took the benchmarks Verx used. These were taken from industry, so arguably these are at least interesting examples to verify. We found just without any work, we could support 8 out of these 15 contracts. Then with a bit of manual abstraction, most of this was just rewriting features we didn't support in our translation or inlining a few advanced features. We were able to support all but one of these benchmarks. In later work, we were able to support the last one as well, but that's outside the scope of this talk. There we go. We were able to verify all of these smart contracts, so that shows our technique worked. And we also injected faults and were able to find counter examples, so we weren't just like, there wasn't like some major issue and we were just saying everything was safe. But the big result here is when we compared the Verx, we actually had at least a 10 times speedup for all but 2 examples. And even on these 2 examples without a 10 times speedup, it was still a bit faster. And most considerably is this example here where Verx took, well, I guess I should say that this is in seconds, but Verx took well over 20,000 seconds, where we were able to verify the same smart contract in 26 seconds. And at the time we did this work, we weren't able to find these interference invariants manually, but an interesting thing is, due to the limitations of edit tools at the time too, people weren't actually trying to verify properties that require these interference invariants. So we found that for all but one example, we could just give users any amount of, like any arbitrary state for the abstraction, and the verification still went through. So that means that a lot of these properties people were verifying back then actually didn't depend on user state. Though in our option example, it was close, like tightly coupled. So there was definitely, we got the impression from this that the kinds of things people were trying to verify was probably limited by the applicability of the tools at the time. And we also found that in all but one example, we could reduce it down to only 10 users, and in the worst case, we had 16. And so in all of these cases, that's way better than 2 to the power 160, so a huge reduction in the state space. Just a few follow-ups quickly. I know I'm running getting close into my time, just on where we are now after this paper came out. So we published a paper a bit later in VMCAR that looked at the more practical aspects of what we did. So we looked at, for example, what a specification language should be. If we could support these things, we call it aggregate properties. With at the time, before we wrote this paper, that just included sums over maps, but we proposed some other ideas, like for example, looking at the maximum value in the map, and that would matter in our option example because the leading bid should be the maximum value in the map. And we proposed a way to prove this using our local bundle abstraction. We also showed that we could support other verifiers besides Seahorn quite easily in like a design that made it so you could just kind of plug these in. And we also, as I said, gave examples where interference invariants were really related to the properties and definitely necessary. One thing we haven't done is that these local bundle abstractions in this work are quite restricted in that we just pick out a few users. We don't allow relations between the users. So for example, some smart contracts might allow one user to delegate privileges to another. So there's kind of like a tree structure now between the users. Another example is having more than one kind of address. So for example, some smart contracts, like you have these things called non-fungible tokens, which have their own unique identifiers. So now the address space has a few dimensions. The same techniques should apply, but we haven't actually either implemented or looked at the failure of that. And But we do suspect that these compositional proofs should be possible because the underlying theory of what we're doing has no assumptions on these restrictions we used in the paper. So to summarize, we frame smart contracts as parameterized systems with users and controllers, and we argue that this is actually how they should be viewed because it allows for a compositional approach to ameliorate the state explosion other techniques were seeing at the time. We introduced local bundle abstractions to generate sequential programs that could be verified, and these abstractions could be computed automatically with static analysis. And we implemented a new tool called SMARTACE to actually do this verification, and found that it outperformed an existing verifier. And finally, all of this is available on GitHub, including our later work in VMCI 2021, and it can be found on a GitHub account. So with that, I'm happy to take any questions. I'll turn it back to the...
All right, thank you, Scott. Any questions? Maybe Sharon.
I wonder if you can show that your analysis has no false negatives.
What was the question?
Can you actually prove that your analysis is sound in the sense that it has no false negatives?
So barring any, I guess, issues with the implementation itself, because translation and implementation are verified, the underlying, I guess, proof system we're using is known to be sound but incomplete. And that's why, for example, I can say that if we say it's correct, barring any bugs, of course, in our implementation, it is correct. But also why I kind of hand-wave the fact that a proof structure might not exist. So if the actual technique is called parameterized compositional model checking, and that is going to be sound but incomplete.
So it's interesting that you generate a C program and then check the C program. Are there any disadvantages of just like using C as this intermediate language here?
So I guess I could say two things on that. So there was actually a trend now in smart contract verification to translate the C and then use SQL to verify it. The thing I didn't really acknowledge here is that the people working on this paper, myself included, actually developed SQL. So the original question we were wondering was, first of all, is SQL actually a good tool to do this? And should there be extensions to SQL and actually make this look better if SQL is treating like a black box? And this paper didn't go into this part, but the answer is, well, it kind of alludes to it, at least it's open question. The answer was SQL, as given here, wasn't the best solution because if you wanted to do like any kind of abstraction, like for example, interference invariance, there was no good interface to SQL to actually specify these abstractions. And then later we actually added an extension to SQL to allow that to happen. So before this work, it wasn't a good idea, but arguably it's good now.
Well. All right, let's thank Scott again.